Chapter 8.3 Laws of Logarithms. Y equals c to the power of x and y equals log c of x are inverses of each other. Recall that for the exponential function, we have that c is greater than 0 and also c cannot equal 1. For the log function, we have that as well. C is greater than 0 and c cannot equal to 1. And then we also have that x will have to be greater than 0. Since c is greater than 0, c is not equal to 1, c to the power of any value y is going to give us a positive x value. So we learned previously that log base c of c to the power of n equals n. So if the argument is written as a power of the base, then that power becomes the value of the log. Then we have that log base c of c equals 1. This is really just the same thing we just saw. C would be c to the power of 1. So then our exponent of 1 becomes the value of the log. And log base c of 1 equals 0. Recall that a non-zero number to the power of 0 equals 1. So we could write 1 as c to the power of 0, and then it's the same law that we saw in the two previous examples. Our exponent on the argument becomes the value of the log. Log c of 0 is undefined. We can write it in exponential form. We'd have c to the power of y equals 0. But if c is greater than 0, there is no exponent that would make c to the power of y equal to 0. So getting c to the power of y equals to 0 is not possible. Therefore, log c of 0 is undefined. And then just a reminder of this exponent law changing from radical form to fraction exponent form. The nth root of x to the power of m, and that m can be underneath the root or outside the root, becomes x to the power of the fraction exponent m over n. That's one of our exponent laws. We have several exponent laws, and just like exponent laws, we also have laws for logarithms. Here are the log laws. We have the change of base law, which says if we have a log that's in base c, we can change that to log base 10 by taking log of the argument and dividing it by log of the base. So log base 10 of the argument divided by log base 10 of the base. I remember this by thinking the big number is on top because it's bigger, small number is below because it's smaller. The product law says that log c of an argument that is a product, m times n in this case, equals log base c of m plus log base c of n. Example, log base 10 of 6 times 11. We can write that as the sum of two logs. It would be log base 10 of 6 plus log base 10 of 11. Next we have the power law. Log base c of m to the power of n is equivalent to n times log base c of m. So we can take this exponent on the argument and we can move it down in front of the log and multiply it to the log. Example, log base 3 of x to the power of 5 can take this exponent on the argument, bring it in front of the log as a product. Then we get 5 times log 3 of x. The quotient law, log base c of a quotient m divided by n is equivalent to log base c of m minus log base c of n. Now here we have a fraction, which means we have a denominator, so we do have to restrict the denominator if we have any variables in the denominator. Example, log base 10 of 2 over 5. We can write that as the difference of two logs, log base 10 of the numerator minus log base 10 of the denominator. Natural log. The natural log is written ln, ln, and it means log base e. And e is just a specific number. It's like pi. It continues on forever and ever, just like pi. But e is 2.71828 ... So it's just a number. And the natural log is log of base e. Example, apply the laws of logarithms to expand in terms of individual logarithms. First one, we have log 3 times 2 to the power of 3. We want to write this as individual logarithms. Yes, we could just multiply 3 times 2 to the 3, and then we'd have one log, but we are using the log laws to separate the product. So we can write this as the sum of log 3 plus log 2 to the power of 3. We've got an argument with an exponent on the second log. We can move that exponent down in front of the log, and we get log 3 plus 3 log 2. Next one is log base 5 of the square root of x. Square root we can change to a fraction exponent, so we write that as log base 5 of x to the power of 1/2. Then we have the power rule. We can take that exponent on the argument and multiply it to the log. Then we get 1/2 log base 5 of x. And we would have the restriction here, since we have a variable as the argument. We would say that x is greater than 0. The argument has to be greater than 0. We also had a radical here, so we want to make sure that what's under the radical is greater than or equal to 0. So for this part, we would have x is greater than or equal to 0 for the radical. But because that radical is the argument, that would just be x is greater than 0, because the argument will not equal 0 in a logarithm. So we just have that x has to be greater than 0. Log of 6 divided by 5 to the power of 6. First we have the exponent law. We can move that exponent from the argument to the front of the log. We get 6 log 6 over 5. Then we have the quotient law. We can write this as the difference of two logs. We get 6 and then bracket log of the numerator, which is 6, minus log of the denominator, which is 5, close bracket. I had to put brackets around the logs because that 6 applies to both logs. Then I can either multiply the 6 in or just leave it factored like this. Log x, y, z to the power of 3. We know that the argument has to be greater than 0, so the product of x, y, z to the power of 3 has to be greater than 0. We have the product law, so we can write this as the sum of 3 logs. We get log x plus log y plus log z to the power of 3. Then we have the exponent law, so I can bring this 3 down in front of this log. Then we get log x plus log y plus 3 log z. And our restrictions, each argument in the 3 different logs has to be greater than 0. So we would have x is greater than 0, y is greater than 0, and z is greater than 0. Then if all 3 of those are greater than 0, we would also have that x times y times z to the power of 3 would be greater than 0. So our original restriction would be satisfied as well. Log a times b all squared. First we have the power rule. I can bring this exponent in front of the log. We get 2 log ab. Then we have the product rule. I can write this as the sum of 2 logs then. 2 bracket log a plus log b. Again, we need brackets because that 2 applies to both of the logs. You can leave it like this, or you can multiply the 2 into the brackets. Then for restrictions, up here we would have that AB has to be greater than 0. So the product of A and B have to be greater than 0, which could mean that A and B are both negative, because that would result in product being greater than 0, or A and B are both positive. But then in our final form, we have a log A, which means that A has to be greater than 0 since it's an argument in a log, and we have a log B, so B also has to be greater than 0 since that's an argument in a log. So our restrictions are that both A and B are greater than 0. Log base 2 of x, y over z. Our restrictions, well, for one, we have a denominator, so we would have that z cannot equal to 0. We would also need the whole fraction, x, y over z, has to be greater than 0 since that is an argument in a log. Let's apply the log laws. I'm going to do the division first. I see that I have a product on the top, but I also have a quotient. So I'm going to do the quotient law first. I get log 2 of xy minus log 2z. Then I can apply the product rule, and I get log 2x plus log base 2 of y minus log base 2 of z. Then for our restrictions, we now have log base 2 of x, which means x is an argument in a log, so x has to be greater than 0. We have log base 2 of y, so y has to be greater than 0. And we have log base 2 of z, so z also has to be greater than 0. If all 3 of those are greater than 0, then that also satisfies x times y divided by z being greater than 0, and z not equaling 0. And these are the restrictions for our variables. Apply the laws of logarithms to simplify each expression as a single log. So before we were expanding to express in multiple logs, now we're going to combine into one log. So we have log 12 plus log 5. They have the same base, they're both base 10, so we can use our log laws. This would be the product law. Product law is where we can write the sum of 2 logs. So we can go backwards. If we have the sum of 2 logs with the same base, we can write that as a product in one log. We can write this as one log, log base 10 of 12 times 5. Simplify that. 12 times 5 is 60, so log base 10 of 60. Log 20 minus log 5. We have the same base. This is a subtraction, so that would be the quotient law. Then we can write this as log base 10 of 20 divided by 5. 20 divided by 5 is 4, so log base 10 of 4. Log x over 2 plus log y over 2. We can factor out 1/2. Then we have 1/2 times log x plus log y. Log x plus log y, that's the product rule. We can write that as 1 log. We get 1/2 times log of the product x, y. And then we have a coefficient in front of the log. That's the exponent law, so we can write that as the exponent on the argument. And we get log of x, y to the power of 1/2. An exponent of 1/2 is a square root, so we could also write this as log base 10 of the square root of x, y. Either one of those would be fine for your final answer. Then for this one, we have variables in the argument. So we would have to set restrictions. Here we would have x has to be greater than 0 and y has to be greater than 0. Here we would have the product of x and y has to be greater than 0, which it would be if x and y are greater than 0. And then here we have a square root. We can't have a negative under the square root. So again, x times y has to be greater than or equal to 0. It would be greater than 0 since we'd have that x and y both have to be greater than 0. So our restrictions are x is greater than 0 and y is greater than 0. Log a minus 5 log b plus 2 log c. When I see a coefficient in front of a log, I should think of the exponent law, and I can move that coefficient to become an exponent on the argument. Then I get log a minus log b to the power of 5 plus log square root c to the power of 2. I can simplify this a bit more. The square root of c, if we write that as an exponent, that means c to the power of 1/2. Then we have log a minus log b to the power of 5 plus log c to the 1/2 and then to the power of 2. 1/2 times 2 is 1, so then we just have log c. Then I have subtraction of the first 2 logs and then addition for the third log. I need to go in order from left to right since in terms of bed mass, addition and subtraction are the same. I can use the quotient law for the first 2. We get log a over b to the power of 5. And then we have plus log c. Then we use the product rule and we get log a over b to the power of 5 times c, which becomes log ac over b to the power of 5. For restrictions, we would have, since we have log a, log b, and log c, we would have that a, b, and c are all greater than 0. We also have the square root of c, so we still need c to be greater than or equal to 0 in that case, but it's going to be greater than 0. Then we have b as the denominator of a fraction, so b cannot equal 0, which it won't because we have b is greater than 0. So our restrictions are a, b, and c are greater than 0. Log of 2x plus 1 plus log of x minus 5. So again, they're both base 10. This is a sum of two logs of base 10. Then we can use the product rule to write them as one log. We'd have log base 10 of 2x plus 1 times x minus 5. I can multiply those binomials together. We get log of 2x times x is 2x squared. 2x times negative 5 is negative 10x. 1 times x is 1x. And 1 times negative 5 is negative 5. Simplify. We get log of 2x squared minus 9x minus 5. Then for restrictions, we have to have the argument from each log greater than 0. So 2x plus 1 is greater than 0, and x minus 5 is greater than 0. Subtract 1 from both sides, we get 2x is greater than negative 1. Divide by 2, we get x is greater than negative 1/2. And then for x minus 5 greater than 0, add 5 to both sides, we get x is greater than 5. Which of these restrictions is most strict? X greater than negative 1/2 or x greater than 5? Well, if x is greater than negative 1/2, it's not necessarily greater than 5. But if x is greater than 5, then it's definitely greater than negative 1/2. So x greater than 5 is the restriction for this log. Use the laws of logarithms to simplify and evaluate each expression. Log base 2 of 100 minus log base 2 of 25. That's a difference of two logs with the same base. We can use the quotient rule to write that as one log. It would be log base 2 of 100 divided by 25. That equals log base 2 of 4. 100 divided by 25 is 4. Then we can evaluate. We can write 4 as 2 to the power of 2. Now, since we have log base 2 of 2 to the power of 2, our answer to that log is the exponent on the argument, which equals 2. So this is the simplified form. So if it says to simplify, you can stop there. If it says to evaluate, then you go to this point where you say what that log equals. Log base 3 of 9 times the square root of 3. We can use the product law to write this as log base 3 of 9 plus log base 3 of the square root of 3. Square root of 3 is 3 to the power of 1/2, so log base 3 of 9 plus log base 3 of 3 to the power of 1/2. We can write 9 as 3 to the power of 2, so log base 3 of 3 squared plus log base 3 of 3 to the power of 1/2. Then we can evaluate each of our logs. Log base 3 of 3 to the power of 2 is 2. And log base 3 of 3 to the power of 1/2 is 1/2. So we get 2 plus 1/2, which equals 2.5, or 5/2. Log base 3 of 54 plus log base 3 of 1/2. We can write this as one log using the product law. We get log base 3 of 54 times 1/2. Half of 54 is 27, so we get log base 3 of 27. 27 is a power of 3. We can write log base 3 of 3 to the power of 3. Then we can evaluate. Log base 3 of 3 to the power of 3 equals 3. Recall from the example from Chapter 8.2 notes, we found the translated equation to be y equals log base 4 of 4x. Using this equation and the log laws, describe another translation that can be applied to the graph of y equals log base 4x to produce the same graph. So starting with y equals log base 4 of 4x, we can apply the product rule to write this as two logs. So we get y equals log base 4 of 4 plus log base 4 of x. Then we can evaluate log base 4 of 4, that just is 1, so y equals 1 plus log base 4 of x. And I can switch the order of the 1 and the log, so I get y equals log base 4 of x plus 1. What does this 1 represent in terms of transformations? That's a k value equal to 1, which means a vertical translation up 1 unit. So if we were transforming this graph, we did a horizontal stretch factor because we were turning this point into this point. But if we didn't have any of those points to go on, we could just look at this as this point here has been shifted up 1 to get here. This point here has been shifted up 1 to get here. So a vertical shift 1 unit up. So we get two different possible log functions that can represent this same red graph, which is a transformation of the blue graph, y equals log base 4 of x. If x equals log base 4 of 5 and y equals log base 4 of 3, express log base 4 of 45 in terms of x and y. So what we want to do here is break down 45 into a product that involves 5 and 3. Now 5 times 3 is 15, which is not 45, but we can write log 4 of 45 is equal to log base 4 of the product 5 times 9. Then we can write log base 4 of 5 plus log base 4 of 9 using the product law. But 9 is a power of 3, so we can write this as log base 4 of 5 plus log base 4 of 3 to the power of 2. And then we can use the exponent law or the power law to bring this 2 in front of this log as a coefficient. And we get log base 4 of 5 plus 2 log base 4 of 3. And then we have that log base 4 of 5 equals x. and log base 4 of 3 equals y. So where we have log base 4 of 5, instead we're going to replace that with x. And then we have plus 2 log base 4 of 3, which equals y. So we get log base 4 of 45 equals x plus 2y. Show that 7 log C4 equals 14 log C2 is true for C greater than 0 and C not equal to 1. 7 log C4, I can use the exponent law and write the coefficient of 7 as an exponent on the 4. Then I get log C4 to the power of 7 equals 14 log C2. I want to get an argument that has 2, since that's what I have here. I can rewrite 4 as a power of 2. It becomes log base C of 2 squared, and then to the power of 7 equals 14 log base C of 2. Then the left side becomes log base C of 2 to the power of 2 times 7, which is 14, equals 14 log base C of 2. Then I can use the exponent law again, bring this down, and we get 14 log base C of 2 equals 14 log base C of 2. So left side equals right side. I didn't know that that's how it was going to go. I just saw that there was something I could do on the left side. I could move this to be a power, and that's where I started. And then I continued from there. Then I saw that I had 2 here, and I could write 4 as a power of 2. Then I just continued manipulating using the log laws until I was able to get the left side equal to the right side. You could have left the 7 in front, changed the 4 to 2 to the power of 2, and then brought down that 2, and you would have 7 times 2 in front, and that would have worked as well and saved you one step, because this really was an extra step that I didn't need, but I just started somewhere and did what I could do at each step and eventually got to the result that I wanted. So let that be a lesson. You don't always know exactly what you need to do or how you're going to get to the end result. Just start with something and then see if you can do one more step and one more step and one more step, and hopefully in the end you'll get to the result you're looking for. Write the expression as a single logarithm in simplest form, state any restrictions on the variables. Log base 2 of x squared minus 9 minus log base 2 of x squared minus x minus 6. This is a difference of 2 logs with the same base. We can write that as 1 log. We get log base 2 of the fraction x squared minus 9 over x squared minus x minus 6. Let's factor the top and bottom of the fraction. Log base 2 of the fraction, the top is a difference of squares, x squared minus 9, so it factors to x plus 3 times x minus 3. The bottom, x squared minus x minus 6, we want two numbers that multiply to negative 6 and add to negative 1, which would be negative 3 and positive 2. Then I can simplify by dividing out x minus 3 on top and bottom. We get log base 2 of x plus 3 over x plus 2. For restrictions for this function, we have a little bit to think about. First of all, we have a denominator. The factors in our denominator cannot equal 0, so we would have that x minus 3 cannot equal to 0, which means that x cannot equal 3. We also have x plus 2 in our denominator. That cannot equal to 0, which means that x cannot equal negative 2. Then we also need our simplified fraction x plus 3 over x plus 2 to be greater than 0, since that's the argument in our log function. There's two ways that a fraction can be greater than 0. Either both the top and bottom are positive, or both the top and bottom are negative. So we need to look at the restrictions for both cases. If the top and bottom are positive, so x plus 3 is greater than 0, that means x is greater than negative 3, and x plus 2 greater than 0 means x is greater than negative 2. This was for both positive. And then we can look at the other case, which is that both top and bottom are negative. We have x plus 3 is less than 0, which means x is less than negative 3. And x plus 2 is less than 0, which means x is less than negative 2. So this one actually has a lot of restrictions because we have some greater than, some less than, some not equal to. So if we look at the greater than restrictions, where we have x greater than negative 3 and x greater than negative 2, which one of those is more restricted? So which one includes the other restriction? If x is greater than negative 2, it is also greater than negative 3. So x greater than negative 2 is our greater than restriction. We also have that x cannot equal to negative 2, but if it's greater than negative 2, then it's not equaling to negative 2. Then for the less than restrictions, x less than negative 3 and x less than negative 2, which one of those includes the other one? X being less than negative 3, if x is less than negative 3, then it is definitely less than negative 2 as well. So for the less than restriction, we have x less than negative 3. And then we also have that x cannot equal positive 3, which is not taken care of by our other restrictions, so we have to include that too. So all of our restrictions together is that x is less than negative 3, x is greater than negative 2, and x cannot equal 3. So we can have numbers that are smaller than negative 3, and we can have numbers that are greater than negative 2, except we cannot have an x value that equals positive 3. That is a very tough one for restrictions. They are usually much more simplistic than that. For log base 3 of x minus 1/2 times log base 3 of x plus 5 log base 3 of x. We can simplify the brackets. We get 4 log base 3 of x minus 1/2 times log base 3 of x plus the 5 can be written as a exponent on the argument, so log base 3 of x to the power of 5. We can also write this 4 as an exponent on the argument for that log. We get log base 3 of x to the power of 4 minus 1/2. We can write the brackets as 1 log log base 3 of x times x to the power of 5. We get log base 3 of x to the power of 4 minus 1/2 log base 3 of x to the power of 6. We can write this 1/2 as an exponent on the argument. Then we have log 3 x to the power of 4 minus log 3 x to the power of 6 to the power of 1/2. Simplify that to log 3 x to the power of 4 minus log 3 of x to the power of 3. 6 times 1/2 is 3. Then we can write this as 1 log. Using the quotient law, we get log 3 of x to the power of 4 divided by x to the power of 3. And we can simplify that fraction. We get log base 3 x to the power of 4 divided by x to the power of 3 is x. All the way along, we have log base 3 of x, so we'd have x is greater than 0, x is greater than 0, x is greater than 0. That continues throughout, x being greater than 0. Then we get down to a fraction. So for the denominator, we have to have that x cannot equal 0, which it wouldn't anyways, since our restriction was that x is greater than 0. So x greater than 0 is our only restriction. The pH of a solution is given by pH equals negative log base 10 of H+, where H+ is the hydrogen ion concentration in moles per liter. What is the hydrogen ion concentration of a lemon juice solution if its pH is 3.2? So pH equals 3.2. We can put that into our formula. We have 3.2 equals negative log base 10 of the hydrogen ion concentration. We can divide by -1. Then we get negative 3.2 equals log base 10 of the hydrogen ion concentration. Recall that for solving logs, we often want to change them to exponential form. So this would be the base is 10 to the power of the exponent is negative 3.2 equals the argument, which in this case is our hydrogen ion concentration. Then we can calculate that. to the power of negative 3.2, which gives us this number. So we have the hydrogen ion concentration of a lemon juice with pH 3.2 is, if we write this in scientific notation, it says 6.3095 blah 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 E negative 4. That means 6.3 times 10 to the power of negative 4. And that was in moles per liter. Determine the pH of milk to the nearest tenth if its hydrogen ion concentration is 3 times 10 to the negative 7. Our formula is pH equals negative log base 10 of the hydrogen ion concentration In this case, that is 3 times 10 to the negative 7. So we have pH equals negative log base 10 of 3 times 10 to the power of negative 7. Then we can just calculate that right side using our calculator. Negative, it's log base 10, so I can just use the log button. 3 times 10 to the power of negative 7. Make sure that's all in the brackets. Enter, we get 6.5228 ... So our pH of milk with a hydrogen ion concentration of 3 times 10 to the power of negative 7 is, rounded to the nearest tenth, would be 6.5. That brings us to the end of Chapter 8, Lesson 3.